So let's go ahead and get started. My name is Marcus Wassmer, and I am the Director of Engineering for Graphics at Epic Games. And I'm here to talk to you today about some work that we've done on the renderer. So over the past year, the rendering team has worked on a large refactor of the mesh drawing pipeline in UE4. And today I'm going to talk about why we did this work, some of the benefits that we've seen, let you know what you'll need to do to update any modifications to the engine that you've done, and then talk about a little bit about where we're going in the future. Firstly, for motivation, one of the things we've seen with UE4 game teams is that they want to make large open worlds in the future with larger view ranges, higher detail, seamless interiors. People want to use more modular construction. And we think that next generation dynamic lighting and shadowing techniques are going to require extra geometry passes. So the bottom line is that in the future, UE4 needs to be able to execute a lot of draws. Secondarily, upcoming technologies need the entire scene's draws prepared, not just the visible set. For example, the DXR ray tracing API from Microsoft requires a shader binding table that has to be built for the entire scene, not just the visible set. And future GPU-driven culling techniques also need to be able to prepare draws without knowing any visibility information. So the bottom line here is that we need to not be preparing the entire scene's draws every frame, because this does not scale with larger and larger worlds. So the main question is, how do we get to a situation where we can draw these large worlds? Well, first, we think we need a draw call merging framework. And such draw call merging needs to be based on RHI capabilities. So specifically, like on DirectX 11, draws can only differ by instance ID to still be merged, which means that we can't have any more per draw, per frame shader parameters and still have successful draw call merging. Instead, such parameters like this need to be uploaded to a buffer and then dynamically indexed in the shader by a primitive ID that can look the information up properly. In addition to draw call merging, we need to do more aggressive caching in the renderer. So, like when we add static objects to the scene, we need to build those draws when they're added to the scene rather than every frame. We want to allow each RHI to pre-build as much data as possible about a draw. For example, the shader binding table entry for DirectX 12, or the graphics pipeline state for, like Vulkan or Metal. This removes some renderer overhead in building static geometry draws every frame and generally makes things more efficient. So before we talk about kind of how we changed the renderer, I think it's useful to go through kind of how UE4 mesh drawing works before we redid everything. So drawing kind of starts in the UE4 renderer with the concept of a primitive scene proxy. And because UE4 is a split game thread render thread architecture, the primitive scene proxy is the view that the rendering thread has of a given object that needs to be rendered. Its data is completely separate from the game thread data for threading safety purposes. From the proxy, we can create what we call mesh batches. And these are either created statically for static objects or via the function getDynamicMeshElements for dynamic objects. So let's take a look at what a mesh batch actually is. So a mesh batch decouples the scene proxy implementations, like the specific user code. For example, landscape proxy has a lot of custom code in it. So we decouple that from the mesh passes in the private rendering code, like the depth drawing pass or the base drawing pass. Because the private code has to work on a generic object without the user code embedded in it. So the mesh batch kind of contains everything that a given rendering pass needs to figure out its shader bindings, like resources and geometry data. And a proxy doesn't know what passes it's going to be rendered in. For example, the proxy doesn't know if it's going to be rendered in shadows or rendered in the velocity pass or any other such pass. So once we have our mesh batches, then we can go through one of our pass rendering functions like render base pass, where we will traverse our static mesh draw list and then render them with code known as a drawing policy that knows how to bind all the data required for a given pass. And then this will generate a set of platform agnostic RHI command list commands, which is a platform independent command layer that we record everything into. Could probably talk about that for a while, but that might be another hour. But once we have this command list, we can finally do the execution for it and make the actual API calls, like the DirectX 11 draw index primitive calls, and do final rendering. So if you look at kind of what the traversal and drawing policy process is, mainly it's building up the pipeline state, gathering the necessary shaders for a draw plus the necessary rendering state, and gathering all of the shader bindings. So it has to walk the material chain, get data from the vertex factory, from the shader map, from the scene, from the current view, etc. And again, since the proxy doesn't know what passes it'll be in, this has to be done kind of every frame. So why do we want to change this system? We've had it for 5 years now. We've shipped a lot of good games with it. And there's a couple of different reasons. First of all, the static mesh draw list uses bit arrays for visibility, which means that these arrays continue to grow based on the number of objects in the scene. And we have to iterate over this array when drawing, which means that the cost of rendering increases with the number of objects in the scene rather than with the cost of things that are actually visible. This makes it particularly poor for very large worlds. Also, there are, in the current code, completely separate rendering paths for static and dynamic objects. And this means that we can't sort drawing between static and dynamic objects, which can be bad for depth sorting or state sorting. In addition, kind of the entire static mesh draw list is templated by shader permutation, which makes the code kind of ugly and difficult to work with and difficult to extend. And then lastly, there's only a single hard-coded frequency for state sharing. So this means that we can't really dynamically instance anything to do draw call merging with the current system. So long story short, yeah, that's the main thing. The current design, or the previous design, just prevents efficient draw merging. And the drawing policy code that was used to actually perform the rendering was very tightly coupled to the draw list code itself, and that needed to go as well. So let's take a look at the new drawing pipeline. So first you can see we just straight up deleted the static mesh draw list and all draw policy code. This is kind of the most major change. Instead, we've added the concept of the mesh draw command and a class called the mesh pass processor that generates those commands, and a generic method to submit them to the command list. So if we take a closer look at the draw command, we can see that this is a small data-driven structure that stores everything that the RHI needs to know for a specific pass, which is what makes it different than a mesh batch. So this is a full, standalone, stateless description of a draw. All of the context of where this draw came from has been removed to make this as small as possible. Although there is a debug pointer back to the original proxy, which is removed in shipping builds. So you can't write any code that relies on this, but if you're debugging the engine and you find one of these things, you can tell where it came from. So this design has a lot of nice properties. For one, it enables more aggressive caching because we can build these draw commands for static geometry one time when we add objects to the scene, which gets us closer to what we would call a fully retained mode, where like the pipeline state object and all shader bindings could be known at load time. We're not quite there yet, but we're a little closer. This design also enables a robust draw call merging framework, which for D3D11, the implementation we're going to call dynamic instancing. And this means that we can merge our draw calls based on the actual data that's used, not based on hard-coded either programmer or artist code. We'll talk about that a little bit later in more detail. So first, let's talk a little bit about the processor that takes the mesh batch and turns it into the draw command. So the processor's job is to build one or more mesh draw commands from the batch. To do this, it needs to select the proper shader. It needs to collect all of the resource pass bindings and vertex factory bindings and material bindings. And again, the main difference here between the batch and the command is that the command is specifically for a particular rendering pass, like a shadow pass or the velocity pass, whereas the batch could be for anything. And so if you would like to implement a new mesh processor to add a new mesh pass to the engine, which some of you may have done before by adding your own drawing policies, it's now a lot easier to do because the processor isn't templated based on shader class. And because it's not templated, we can use the same code for both the cached and dynamic paths. So let's take a look at a quick example. The depth pass, or just the base depth pass that's in the engine. And here we can see the depth pass processor. There is a little bit of copy and paste boilerplate for making a new one of these things, but it's a lot smaller than the old code. We won't spend too much time looking at the code slides. You can just download the code from GitHub and take a look at it if you like. But the main things that we need to do is fill out the add mesh batch function here. And the two main jobs are to do some filtering to remove objects that should not be in your pass. For example, since this is the depth pass, we remove objects that are translucent. And then secondly, it needs to do shader selection, as you can kind of read there later if you grab the slides. And then this slide shows off the processing function that actually calls a shared function that helps you implement these passes called build mesh draw commands, which is a function that's shared amongst all of the mesh processors, and we'll get to a slide for that in just a minute. But for some data, like that's it for a new custom geometry pass. If we compare to the old design of the renderer, the depth drawing policy and all the related code was about 642 lines of code. And the new mesh processor is not even 100 lines. That's like 6 times less code to implement a geometry pass. For the base pass, it's a little more complicated. It was kind of only a 4x reduction, but it's still a lot easier to extend the engine in this way in the new system. So I did mention the build mesh draw commands function. This is one of the reasons why it's so much less code to implement a new geometry pass, because this is the code that collects all the shader bindings, and it can be completely shared between all the passes. And this removes just tons of boilerplate when you're adding new mesh code. The main change that allows this is that parameters are now gathered into a shader binding structure rather than being set directly on the command list so that they can be executed later. Okay, so now there's also a location where we can sort the mesh draw commands amongst each other. And because the draw commands are stateless and have no context, they don't know if they're static or dynamic, and it means we can sort all different types of objects together kind of in one run, which is a nice property that we get out of this. And then finally, after we have sorted our commands, we can call a generic function to actually draw things. This is again a difference from the old drawing policy code, where every drawing policy needed custom code to do all the drawing. But because every mesh command has everything you need to do a draw, there can just be one common function that knows how to draw mesh commands now. So if we take a quick look at that, there are also other nice properties. So the submission now scales completely with the visible set. The only thing that it has is the array of actual draw commands that are visible. In the old system, we had to iterate over the whole scene bit array, which scaled with the scene set. Also, this is very easy to split into even tasks because we just have one linear array. We know that every draw is going to take the same amount of time to perform, so we can just split these things evenly into task threads and be sure that the load balancing is going to be correct. So if we contrast this with the old draw list, we required to scan over the whole bit array and break up non-contiguous data, and also we didn't really know if it would take longer to draw one thing versus another, so you'd end up with load balancing problems. We also know that because the draw commands are complete and final, all that they're going to do is write to the command list, which means that we know that they're side effect free. So we no longer have to do kind of silly things in the renderer like we used to, like taking snapshots of scene render targets array, which might be modified, or build local uniform buffers. This makes it trivial to parallelize because we know that there's no side effects. One nice property of the submit draw commands is because it's fully generic, we can do things like filter out redundant state setting above the RHI command list level. Most of the RHIs implement their own redundant state filtering internally. However, it's still useful to do it at a high level like this because it reduces the load on command list execution. We found, let me see what's on this. Yeah. So we found in testing that this state filtering was probably worth about a 20% performance increase over not doing it. Okay. And then even without any draw call merging, submitting draws this way is much faster because we have cache coherent traversal. The draw commands come out of linear contiguous arrays, and their small design means that we get really good behavior out of modern CPUs that have good prefetching. This is something that's very valuable on consoles and high-end PCs. Okay, so let's talk a little bit about how the caching works. Since the majority of our worlds are made up of static meshes, preferably we don't want to be figuring out what shaders and what bindings are done every frame. Instead, we want to generate our draw commands up front and just do selection each frame. Because you can imagine in theory that we could generate draw commands every frame and still get some win. But the best win is to not create them every frame and cache them where we can. But to do this caching, it kind of requires that anything referenced by the cache command must not change frequently. Because if things change frequently that are referenced, they have to be invalidated and recreated anyway, and you wouldn't get a benefit out of caching them. So for the engine, this means we need to leverage our uniform buffer structure as an indirection to make this possible. So let's look at an example here. So in the old design, the engine would create a new view uniform buffer every frame. This is the structure that has data about like the camera projection and things like that in it. So when we create a new one of those every frame, that would mean a new pointer that each draw command would have to refer to. So when we create a new one, we would have to invalidate, if there were 10,000 commands in the scene, we'd have to invalidate and recreate 10,000 draw commands every frame. However, instead of doing that, we can just keep our single view uniform buffer and update its data on the GPU every frame. This allows every draw command to keep the same pointer, and we don't have to touch them. If you're familiar with the RHI, you know that there was no function to do this, so we had to add an RHI function to update uniform buffer data in place on the GPU timeline, and this allows us to have a stable parameter ref whose contents change. And there are various uniform buffers that are related to draws that need to be updated in this way. Like there are primitive uniform buffer, material uniform buffer, material parameter collections, et cetera, et cetera. So again, if things change that would affect rendering that require invalidation, you need to do that, or you'll start rendering the wrong things, or maybe re-rendering with resources that have been deleted, which can cause a crash. This kind of thing was mostly already handled because static mesh draw lists had a lot of the same requirements. However, since we now cache shader bindings, you have to update these instead of recreating, or you'll crash. So you need to invalidate the cache. So this is kind of like for custom code that you've written, this is something that you need to be aware of. If you have written custom code to do custom rendering that you're trying to insert into the system, there's a validation define that you can flip in the code and recompile the engine, which should hopefully kind of crash you where the bug is rather than later deep inside the engine. Most of you probably won't need to do this, but people that have modified the engine may find this useful. Okay, so let's talk about what types of things support caching. So basically, it's only local vertex factory. We can only cache objects that don't require a view and are constant every frame. Local vertex factory is the one that's used for static meshes. Things like landscape changes how it renders based on where the camera view is, which means that you can't cache it when you add the landscape to the scene. And similarly for the rest of these types, like the instance static mesh or hierarchical one, they're very view dependent, and so you can't do any caching. So what we end up with is 3 different caching paths through the renderer. So the slowest one is fully dynamic relevance, where we kind of create a mesh batch and a draw command and do RHI rendering every frame. So this is things like Niagara particles or cascade particles, which are completely dynamic and change all of their geometry and perhaps shader bindings every frame. The second path is kind of static relevance, but the view is necessary. Again, this is kind of like landscape. So in landscape, we can cache the mesh batch, but there's no way that we can cache draw commands and still get correct rendering. And then finally, for static relevance where we don't need the view, like regular static meshes, we can cache both the batch and the command. And this is the new path, which is now the fastest path. So if we look at kind of the high level of a single frame, when we add something to the scene, we go ahead and generate all the mesh draw commands for the primitive, like for all LODs. If something changes globally in the system, like we added or removed the skylight, which requires us to pick new shaders, then we have to invalidate and recreate all of the draw commands. Then in init views, where we do visibility, we kind of walk each primitive. If it's static, we compute its LOD, and we add the cached command that we already had to the visible list. If it's dynamic, we collect batches and generate commands with getDynamicMeshElements and the mesh processor. And then finally, we can, go into one of our passes and, render things like for depth pass or base pass. All right, let's talk in some more detail about draw call merging. So for D3D11, there's really not too many ways that you can do merging. The main thing you want to do is make draw instance calls. This means that on D3D11, the only thing that can change between the merge draws is the instance ID that's automatically generated in the shaders. So we'll call the merging that we can do dynamic instancing. We think this is easy to implement and prove out the pipeline and kind of has the highest impact across the engine because it will work for many RHIs. More modern APIs like DirectX 12 have functions like direct execute indirect. And with a function like this, you could potentially change state or in the future, maybe even shaders in between merge draws. But we're leaving that for a future exercise at the moment. So with our dynamic instancing framework, we can robustly merge by comparing our mesh draw commands. They're not coupled to any high-level code, and they're all completely generic. The main advantage here is that content creators don't have to opt into this process. They no longer have to create like instance static mesh components and manually choose what is going to get instanced. Instead, we just automatically merge at runtime what can be merged from the visible set. However, you don't want to be spending time comparing all the draw commands every frame. This would be very, very slow and probably worse than just not merging them. So instead, because the draw commands are stateless and don't change, we can assign them state buckets when we cache them and add to scene time. And this means that the actual merging operation is just a data transformation on the visible list. So any commands in the same state bucket just get replaced with a single instanced mesh draw command. Okay, so now we have a framework that can do mesh draw merging, but it won't actually do so unless we make some changes to how the renderer works. Mainly, we need to get rid of per draw bindings, because if a draw command has unique bindings, it can't be merged. So there are multiple changes that we needed to do to make this happen. One major one was creating the new pass uniform buffer frequency. So the old code in a draw policy, when it was drawing, would check a draw and see if it needed to bind, for example, the debuffer textures or the eye adaptation textures, if those were required. And because of that, every draw would potentially get a unique set of bindings. However, the debuffer textures and eye adaptation textures are constant. They don't change. It's the same pointers, the same data for all draws for the whole pass. So we can actually extract all of those and put them into a single uniform buffer so that we can have one single binding for these types of objects for everything in a pass. And you can see some of the examples here. There are more. However, there are still some remaining per draw bindings because some things actually do change per draw. For example, previous local to world matrices for velocity, some dithering LOD state, like actual primitive data where you hold the transform for your object is obviously different for every object, and a few other things. And we needed to remove these to get merging to work properly. So the solution to that is to upload all this data to a single scene-wide uniform buffer and then dynamically index them from the shader. So instead of every object having its own primitive uniform buffer with its transform, we have a scene-wide buffer that has the transforms for all objects. And that means we have a single binding for all objects, which can be merged. So we call this system GPU scene. And it has a primitive data buffer, and it uses a GPU T-array implementation with dynamic resizing. This is actually a useful implementation for any graphics programmers out there. You might find other uses for it. It's pretty handy. But the render thread here tracks primitive add, updates, and remove operations, and then uses the compute shader to only operate on the deltas of the big buffer every frame, because you don't want to reconstruct this whole buffer every frame. It would be too slow. So now all shaders that need to access this data need to access it with a new primitive ID and go through a little function macro. Because this system is only supported by the vertex factories that can do caching, basically. So for the moment, that's still just local vertex factory. So we abstract away the gathering of the data with this little macro and get primitive data. And that might be important for upgrading the engine a little bit later. So hopefully, if I'm being clear, some of you might wonder, how do we get the primitive ID into this giant scene array if DirectX 11 is only giving us the instance ID? Because every draw needs a different offset into the primitive ID buffer in the scene. So one way that we can do this is by adding just like a single global constant buffer shader parameter per draw. This was kind of slow, though, and kind of defeats the purpose of a lot of the caching and merging work that we did. Fortunately, there is a solution, and that is that setStreamSource accepts a dynamic offset, so we can do something a little bit clever by creating dynamically every frame a vertex buffer that works on instancing frequency that holds the offset for each instance draw inside the vertex buffer, so that every instance of the draw will be able to look up the offset into the scene-wide buffer. And this can be done basically for free. It's just another geometry binding and doesn't require a whole lot of extra work. Okay, so let's kind of see after all that how effective things are. So the rendering team internally uses a little project that we call the GPU perf test. And the GPU perf test project is basically just a little city of Fortnite extracted out of the Fortnite project and put into just like a little static separate project without any of the game code. So this gives us a useful place to operate, to iterate on engine changes and measure performance changes and visual fidelity changes in a fast manner. Like you can cook GPU perf test in a fraction of the time that it would take to cook Fortnite, for example. So in this test, our initial results were that the merging effectiveness caused about a 2x reduction, 2.2x reduction in draw calls in the base pass, and about a 2x reduction in the base pass. The reason that the base pass is a little less is because it has more complicated features and more things that can change per draw, which results in less merging. But the real thing that we wanted to test for this system was how is it going to behave in potential future worlds that are very big. And being lazy programmers, one of the simplest ways to do this is to duplicate all of the data inside the perf test 3 times and then turn off distance culling. So this quickly gives us a project that has many thousands of draws without having to go to an artist to generate more content for us. So in this more extreme case, we've had very good results with merging, where we got almost a 10x reduction factor in the base pass or in the depth pass, and almost a 5x reduction in the base pass. However, there are a few things that will cause merging to fail. For example, if you're using baked lighting and you have light maps with small textures, you can end up with different objects needing a different texture for your light map atlas, and this will break draw call merging because you have a different texture for different objects. There are things you can tweak if you find that this happens. You can tweak some of your light mask settings to get a better result. Also, per component vertex colors. So if you use vertex paint to paint unique data onto your world, this is currently not mergeable, as the engine does not try to merge vertex color data into the GPU scene. So this may break merging on your project. The speed tree wind node, if you're using a lot of speed tree wind, your trees will not get merged. And then also, if you're using the old sparse volume lighting samples, or also known as the indirect lighting cache, movable components that are using that system won't be merged either. However, movable components that use the new volumetric light maps can still get merged. Okay, so that's kind of some merging stats, but let's look at some real performance results on something like a PS4. So again, we're using GPU perf test. And I want to reiterate that the numbers I'm talking about here are only the time spent doing the drawing on the render thread. But with that said, you can see we had about a 6x reduction in time on the depth pass and almost a 7x reduction on the base pass for the drawing time on the standard view of GPU perf test here. And that's a really great result. That's kind of what we're looking for. And then in the more extreme case that was meant to emulate future large worlds, where we duplicated things 3 times and turned off the culling, it was even more impressive. It was more like a 13x reduction for the depth pass and an 11x reduction on the base pass. So this is exactly what we wanted to see. We were very pleased. I'd also note that we use a PS4 for performance testing like this because it's kind of a standard candle. Like everyone that has a PS4 can get the same results, whereas if you're on a PC, it kind of depends on what you're running and what your hardware is. However, there are a lot of caveats with those results. So don't go thinking all of rendering is now 13 times faster. The GPU perf test scene is pretty much a best case result. It's very modular. It's made up of the Fortnite pieces, which instance very well. There's a fairly limited mesh variety in that scene as well. And again, we're only showing the drawing speed up, not the full frame. Also, because we parallelized the renderer about 2 years ago, we were already doing rendering in parallel tasks anyway. So when you've had a small enough number of draws, they really weren't on the critical path for the frame. So the gains here really only become significant when you have more than 2,000 draws in your frame anyway. And that's because init views, or our visibility calculation, is still kind of dominating the render thread. Improving the init views time is one of the next things up on the rendering team's list to do. So also, because this was such a big change, there are some things in the engine that did not survive the refactor. For example, pretty much all deferred primitive update mechanisms have been removed. They're just incompatible with retained mode. You can't cache a draw command when you add something to a scene and then say, oh, I'm going to change it later. That's just against the design. So things like defer uniform buffer updates until visible simply don't function anymore. Also, if you upgrade to 422 and you find that your materials don't compile anymore, it may be because you have a custom expression that is accessing primitive data. And if it is, it's a very simple change. You just need to make the new call to get primitive data and use that instead of just primitive.member. So something to check if you upgrade and everything is using the default material all of a sudden. Another thing is that the forward renderer now only supports a single global planar reflection. So if anyone's using the desktop VR forward renderer, that's something to be aware of. And then finally, I want to reiterate again that this is not necessarily a silver bullet. Current UE4 projects may not see any benefits. For example, if draw call performance is not on your render thread critical path, or if your scene is mostly unique materials, you won't get a speed up from auto instancing. At the high level, you're looking for things that are using material instances, not unique materials. Still, if you're dominated by init views because of too many visibility requirements, you won't see a speed up. And currently, the mobile renderer does not do the draw merging. However, we are implementing this for 4.23, so it should be available in, I think it's shipping in August sometime, so it should be later this year that will work on the mobile renderer. Okay, so all those caveats aside, we do have some testimonials from users who ended up with good results from this system. For example, Joe Wintergreen in here, let me use his results. So he's got some scenes where just upgrading to 422, I saved like 1,000 draw calls and 1,200 draw calls off of these two scenes with no changes to any content, which was a nice speed up. And probably most impressively, the game Shores Unknown have very modular data for their game. So they had a scene with something like 18,000 draw calls that was running at about 30 hertz. And just by updating to 4.22, the draw call merging and auto instancing brought that down to 2.3 thousand. So it kind of immediately went from 30 hertz to 60 hertz. Again, it's a best case result because of the way that this level is constructed. But it was nice to see that we did get the best case result when it was possible to do so. So hopefully some of you in the room will see some benefits. And that's kind of it for my presentation today. It looks like we have time for some Q&A and a few questions. So if you have questions, please put them in and we can try to answer them here at the end.